You might wonder, what does the autocovariance function look like? What does the autocorrelation function look like for white noise? Well, we might want to recall the definition of white noise. It's a stationary time series, and for it, the expected value of the product of any two quantities is the square of their mean plus the variance times the Dirac delta function of the difference in times. Delta of h is the Dirac delta function, mu is the expected value, the mean, sigma squared is the variance. If we use index values instead of actual time values, we'd have the discrete Dirac delta function of the difference in index values. Now that means that the autocovariance function is not zero only when the lag is zero. At lag zero, the autocovariance function is the variance. At lag which is not zero, the autocovariance function is zero. It follows that the autocorrelation function has the especially simple form. At lag zero, the autocorrelation function is 1. At lag not zero, the autocorrelation function is 0. And that is an essential, in fact, a defining property of white noise. More compactly, we can just write that rho of h is equal to delta of h, where delta is the discrete Dirac delta function. This very simple behavior, it gives us a clue whether a time series that we observe might be white noise. Suppose we had some estimate of the autocorrelation function based on data. We could call it rho hat of h. By the way, putting a hat over a variable name is a common way of indicating an estimate of it based on observed data. It's not universal notation, but it's pretty common. If the time series is white noise, then the true autocorrelation function is rho equals the Dirac delta function. Therefore, the estimated or sample autocorrelation function should at least approximately be equal to the Dirac delta function. Suppose we have n data points in an evenly sampled time series, so the index values range from 1 to n. A useful estimate of the sample autocovariance function is called the Yule-Walker estimate. We just take the product of each value's difference from average times the value that many time steps later difference from average. We take those products, we add them all up, and we divide by the number of data points. Not the number of terms in the sum, but the number of data points. This gives us the estimate of the autocovariance function at lag h, which is known as the Yule-Walker estimate. By the way, x bar is the sample mean, not the true mean. It's the arithmetic average. You just take all the values, add them up, and divide by how many there are. The Yule-Walker estimate happens to be a biased estimate. That is to say, its expected value is not the true value. But in spite of this drawback, the expected value is approximately equal to the true value, and as you get more and more data, it gets better and better. Now that's the Yule-Walker estimate of the autocovariance function. The Yule-Walker estimate of the autocorrelation function is just the ratio between the autocovariance estimate at lag h and the autocovariance estimate at lag 0, which I could write out fully with this equation here. Now for white noise, the variance of the Yule-Walker estimate itself is approximately 1 divided by the number of data points in the sample, unless the lag is 0. If the lag is 0, the Yule-Walker autocorrelation function is gamma hat of 0 divided by gamma hat of 0, which is going to be exactly equal to 1 every time. But unless the lag is 0, the variance of the Yule-Walker estimate is just about 1 over n, with n the number of data points. The Yule-Walker sample autocorrelation function, like the Yule-Walker sample autocovariance function, is a biased estimate, but again, the bias is small. The Yule-Walker estimate is a good estimate, and the Yule-Walker estimated autocorrelation will approach the true autocorrelation as the number of data points approaches infinity. Now this gives us an eyeball test for white noise. It's not an exact strict numerical test. We'll get to that later. But it's an eyeball test for white noise. If we're given a sample, compute the sample autocorrelation function for a bunch of lags. For lag 0, both the true and the sample autocorrelation function are necessarily equal to 1, but for non-zero lags, if it's white noise, the sample autocorrelation function should be equal to 0 within its error limits most of the time. Not all the time, but most of the time. At 95% confidence, the error limits are about 2 standard deviations around 0. Now, the variance of the sample autocorrelation function for white noise is approximately 1 over n. The standard deviation is approximately the square root of 1 over n. So the sample autocorrelation function should be between negative 2 times the square root of 1 over n and positive 2 times the square root of 1 over n for most lags, about 95%, which we test. So the sample autocorrelation function for white noise will approximately follow the normal distribution. All of this is only approximate, but for a decent sample size, the approximation is usually a good one, and as the sample size gets bigger, it gets better. In fact, the Yule-Walker estimates are asymptotically normal. Here is some white noise. In fact, this is IID Gaussian noise. I generated 1,000 data values and plotted them here. I then computed the sample autocorrelation function using the Yule-Walker estimate, and that gave me this. As you can see at lag 0, the sample autocorrelation function has the value 1. It has to every time. At lags above 0, they're very low. Most of the time, they're between the upper and lower dashed lines, which mark the 2 standard deviation limits around 0. A few of them poke a little bit outside those limits, but that's to be expected. Random quantities will exceed the 95% confidence limits just about 5% of the time. So here we have a case where the eyeball test, it's not a strict test, it's not a precise test, but it gives us an idea, and it tells us that based on autocorrelation, these particular data give the appearance of probably being white noise.